So to me, a big question about this whole second order condition thing or positive definite is the definition involves checking all vectors h that are not zero. That's going to take a while. There's an infinite number of them. So can we boil it down to something else that's easier to check? So let's think about that. We're wondering, is H transpose QH always positive, for example, or never negative? Let's take a little bit of a shortcut and just write QH as some vector little q. It seems like a small enough change for now. So we're asking, when can I say that H times Q is strictly positive, let's say. Let's start with a special case. What if H and Q happen to be equal to each other? Then HQ is HH, and the dot product of a vector with itself is the sum of the squares of each of the components. And the sum of squares has to be bigger than 0, unless h is 0, but we said that h is not the 0 vector. So if we happen to have an h that was equal to q, then we could say this thing is always positive. That seems a little bit too special of a case. What's a slightly less special case? Well, what if h and q weren't equal to each other, but one was a scalar multiple of the other? So if q was some scalar multiple of h, then hq would be h times a scalar times h, and then writing that dot product out component by component would be like this. I can move the scalar out front. And would this be always positive like that was always positive? Well, as long as a was positive, this would always be positive. And if a was negative, it would be a negative times this always positive sum. And so in that slightly less special case, we could still say that that vector product, which is actually kind of this matrix product in disguise, would always be positive, for example. So does that seem still kind of special? Like, what's the chance that I would happen to choose an h that was some matrix times itself times a scalar? Let's look at that condition again. We're saying, what if I chose h such that when I multiplied it by a matrix, I got back the same vector but times a scalar. So it was either stretched out in the same direction, or sometimes in maths the same direction actually could be the opposite direction. If a is a negative value, then we're kind of pointing in the same direction but in a negative way. So we have to kind of allow for that. Does it seem kind of strange that there would be some vector that when I multiply it by a matrix, I get back the same vector but stretched in the same direction, or stretched negatively, or maybe not stretched but the same direction but not quite as far, like a was between 0 and 1? Well, we've actually probably seen that before, although not all classes cover it. That is basically the eigenvalue-eigenvector relationship. So you might have seen it like this. If x is an eigenvector of a square matrix A, and lambda is the eigenvalue associated with that eigenvector, that by definition means that when you multiply the vector by A, you get back the same vector, just longer or shorter, and possibly negatively longer or shorter. And if x was 0, then this would just always be true, and so that's boring, so we don't allow x to be 0 here. So this whole question of when this product is positive seems to be related to eigenvalues and eigenvectors. We don't allow x to be 0, but the eigenvalue can be 0, the lambda can be 0, and that causes some interesting things to go on. Let's talk more about eigenvalues and eigenvectors in the next video.